Hello everyone, welcome back to my channel. Today also we'll be talking about equilibrium, but today we'll be specifically focusing on equilibrium constant. So you will be using the knowledge that you gain through this lesson a lot in the future whenever you're trying to calculate equilibrium constants or different concentrations of some reactants or products in an equilibrium mixture. So without further ado, let's get on with the lesson. Why we should know the equilibrium constant? The answer is given here. It is important to know the relationship between the concentrations of reactants and products in an equilibrium mixture, and how to determine the equilibrium concentrations from initial concentrations, and what factors can be exploited to alter the composition of an equilibrium mixture. So whenever there is a reversible reaction, sometimes you have the requirement of figuring out what the composition of the equilibrium mixture is. Let's say you're starting with products, and then you have to figure out after obtaining an equilibrium, what is the final equilibrium mixture's reactant and product concentrations. Or if you, let's say, there's a product that you need to obtain, and unfortunately the reaction that produces that product is a reversible reaction, then you have to figure out in which ways can you shift the equilibrium point more towards the products end, so that you get more of the products and not more of the reactants, right? So to understand how to manipulate the equilibrium, or understand what kind of concentrations that you might be getting out of a reaction, you need to understand how to calculate equilibrium constant. Law of chemical equilibrium and equilibrium constants. So two Norwegian chemists called Gullberg and Wage in 1964 carried out experiments. Actually, they must have been carrying out experiments even way before that, but in 1964 they came up with a theory called law of mass action. So it suggested at a fixed temperature, the rate of a reaction is determined by the number of collisions between reactant molecules present in a unit volume. So reactant molecules present in a unit volume has another name that we have learned, concentration, right? Which generally referred to as active mass. So what they said was the rate of a reaction depends on the concentration. In simple words, that is what they said through law of mass action. So law of mass action, according to that, concentration is proportional to the rate of a reaction. So therefore, you can just write it as, now I haven't actually broken down the meaning of each of these symbols, but I'm pretty sure you're familiar with it. R normally stands for the rate of a reaction, C stands for the concentration of a reaction. So you can say rate of the reaction is directly proportional to the concentration of the reactants. So as you may know, in mathematics, you do not leave the proportional mark like this and call it an equation. To make it an equation or statement, what we do is we bring in a constant, because since R is directly proportional to concentration, you bring in a constant. We normally use K. So then you have a statement like this: R is equal to K into C. So this K has a name, we call it the rate constant. Right? So this information is key in understanding the next few steps. So R is equal to K into C. K is rate constant, C is concentration. Consider the following reaction. A plus B goes to C plus D, and now this is a reversible reaction. That means there's a specific rate initially, let's say at some point which is not the equilibrium point, there will be a specific rate that A and B those are reactant molecules, will come together to form C and D. So for that particular reaction, the reactant constant is Kf. F stands for forward reaction. So Kf is the reactant constant for the forward reaction. And then for the backward reaction, C and D will be the reactant molecules, and then they will come together to form A and B. Right, so that is the reverse reaction. So for the reverse reaction, you have equilibrium, rate constant, you have a rate constant called Kr. Please notice that I have used simple K when it comes to talking about rate constant, right? Forward reaction rate can be expressed by taking the concentrations into consideration. Now we know in the previous slides we learned rate is equal direction proportional to the reactant concentrations. So R is equal to K into reactant concentration. So here we are writing for the forward reaction an equation which is RF is equal to Kf into concentration of A and into concentration of B. So this first equation tells us about the rate of forward reaction. For the backward reaction, or we call it the reverse reaction, the rate would be expressed as RF equals to Kr into C concentration into D concentration. So that will give you the reverse reactions rate. So at any given time, we can figure out the rate of the forward reaction and the backward reaction if you know the concentration of the reactants that is present in the mixture. So having this information kind of allows us to come to the next point. You know, at equilibrium, whenever a system obtains an equilibrium, forward reaction rate and the backward reaction rate becomes equal. So when that happens, RF will be equivalent to the value of RR. R stands for the reverse reaction in this case. So rate of the forward reaction will be equivalent to the rate of the backward reaction. Now, keeping that thought in mind, let's expand on this thought, like forward reaction rate is equivalent to backward reaction rate. So if you kind of write the statements that we wrote in earlier, the statement for RF and statement for RR, you can make them equivalent to each other like this. And then if you kind of isolate the rate constants to one side, you can see Kf, or rate constant, forward rate constant divided by the rate constant of the backward reaction is going to be equal to this particular statement. Concentration of C divided into concentration of D divided by concentration of A into concentration of B. So that means product's concentration divided by the reactant's concentration. So you know Kf and Kr, or in other words, the rate constants are also constants. That's why we call it constant. That means their value do not change throughout time if the reaction conditions do not change. For instance, if the temperature and the pressure of the system remains equal or remains constant throughout the reaction, the the rate constants will not change. So they are a fixed value. So this statement, Kf divided by Kr, has a constant value, right? So this particular constant value is what we refer to as the equilibrium constant. Again, the same thing can be written as this. Now you can see the relationship. Since this is called the equilibrium constant, the values for Kf and Kr is equal to the concentrations of products divided by concentrations of reactants. So this is the most commonly used equation in calculating equilibrium constant. Concentration of products divided by concentration of reactants. Now we are going to talk about the right or the proper equilibrium constant expression. We learned how we came to Kc value earlier, but there's a little bit more to it than we explained in the previous slide. So when scientists actually did this particular experiment, and now they figured out, okay, there's some sort of a constant that tells us about equilibrium constant that we can obtain through calculations related to concentrations of reactants and products. But when they observed the reactant and product concentration ratios at equilibrium, sometimes they did not get a constant value. For instance, for this particular reaction, for N2O4 going into NO2, when they actually took a look at the nitrogen dioxide concentration divided by the nitrous oxide concentration, they didn't get a constant value. According to this particular equation that we discussed in this slide, you should get a constant value. But when they observed it, it was not the case. They started getting random values. But they also made another observation. If you raise the stoichiometric coefficient that is present in this balanced equation into the power of that particular substance's concentration, and then divide that by the product, the reactant concentration, you get a constant value. So then they realized it was just not the concentrations that you should take into consideration. The stoichiometric coefficients also play a part, and that the stoichiometric coefficients has to be raised as a power into the concentration. So then they came up with the equilibrium constant expression for reaction. This is shown in the slide, right? So this particular equation summarizes everything that I've been trying to say just now. So simple letters, simple A, B, C, and D represent the stoichiometric coefficients of this reaction. Let's say it's a balanced reaction now, and they have been raised into the power of the concentration of each of the substances. And when you do that, you get the proper equilibrium constant. So this is what the equilibrium constant is all about, right? This is the final proper equilibrium constant expression, and using this you can find out the equilibrium constant for any equilibrium reaction, and we'll be using this for the most part of the lesson. Now, just to understand it better, we have another example that is given here, which is an actual example. Nitrogen reacting with hydrogen to become ammonia. So one nitrogen molecule reacts with 3 hydrogen molecules and produce 2 ammonia molecules. Now you can see how ammonia concentration has been raised to the power of 2 because stoichiometric coefficient is 2, and then the the reactants concentrations are mentioned below. They are also raised to their stoichiometric coefficients as its power. So then you get the K.C. value. But you have to understand, depending on how you write the chemical equation, the equilibrium constant that you calculate will have a different value. For instance, if you have, since this is a equilibrium reaction, you can just write it the other way around. For instance, you can write it as, let's say, initially when you were doing this reaction, you did it by taking nitrogen gas and hydrogen gas and putting it into a container and watching it obtain equilibrium. That's one way to do it. The other way that you can do it, taking ammonia gas and giving it the conditions to obtain the equilibrium and producing hydrogen and nitrogen as a result, right? So if you do it, if you do the reaction starting from the products, how you normally write it is the other way around. Now ammonia going into nitrogen and hydrogen. So if you write it like that, then the expression for equilibrium constant will also change. So then equilibrium constant expression would be written the other way around, the reciprocal of the original K.C. that we wrote here. So normally we write the reverse directions equilibrium constant as K-C, right? So it is equivalent to the reciprocal of K.C. You can see it here. To kind of make sure that we understand all this quite well, there is a small example question given here. I got this question from the resource book of that is given for G.C.E. advanced level students by the NIE. So you can actually, I think I have linked it below in the description, so you can go and check out the resource book, and in the resource book you will find this as the first example that they have given. You can see ammonia is formed by nitrogen and hydrogen. At equilibrium, you can see the concentration of ammonia is given. So nitrogen is given, concentration of hydrogen is given, and concentration of ammonia is given. The key to understanding what you should do is figuring out whether they have given these concentrations for the equilibrium mixture. If it is not the equilibrium mixture, sometimes it is not going to be that useful, because we are trying to find out the K.C. or equilibrium constant. So to find out the equilibrium constant, you need the values of each of these reactants and products or their concentrations when the system is at equilibrium. So if the system is not at equilibrium, these concentrations cannot actually help you find the equilibrium constant. So you can very clearly see in this question, they say the following concentrations were measured for an equilibrium mixture. That means the system has obtained an equilibrium of nitrogen, hydrogen and ammonia. So calculate the equilibrium constant for both forward and reverse reaction. So both forward and reverse reaction, that means Kc and K-C. So they have done it here. You can very clearly see. They have substituted the values very carefully, and you have to observe how they have substituted the not only the values but also the units. So whatever the power that is present here belongs to the units as well. Don't forget that. So when you finalize on the answer, you can see all the units, they have been properly solved, and you get for most of the reactions they will have a unique unit for the equilibrium constant. There are two ways in which you can calculate the equilibrium constant for the reverse reaction. One is just using the conventional method of again substituting the equilibrium concentrations and finding the value, or else you can, since you have already found out the Kc value, you know the reciprocal of Kc is going to be the K-C value. So you can just take the reciprocal of the Kc value, which is going to end up giving you the same answer. So they put a note saying, see the changes in the magnitude as well as the units when the equilibrium constant is defined in two opposite directions in the reaction. The equilibrium constant for a reaction written in the reverse is the inverse of the equilibrium constant for the reaction as written originally. So basically they are also saying the same thing. When it is written in the reverse direction, you have to take the reciprocal of the original Kc value. So that is it for it today, guys. That's it for today. So we'll be coming with another lesson the next week, and I'm having a little bit of a feedback on some students. Actually, they asked me to do some lessons on G.C.E. ordinary level chemistry as well. So specifically, some mentioned that they have issues with balancing equations and stuff like that. So I'm actually planning on separately carrying out another series of videos explaining difficult lessons for G.C.E. ordinary level students, because they will most probably be sitting for ordinary level exams at the end of this year. So please make sure you subscribe to this channel, and if you have any questions, don't hesitate to comment down below. And we'll be looking at the connection between the equilibrium constant and Gibbs free energy in the coming lessons. Alright, stay safe and keep learning.